Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Today we're doing a deep dive into, well, one of the most revolutionary ideas in all of modern physics, the particle nature of light, or, as we know it, the photon. This is from Unit 11, Dual Nature of Radiation and Matter. And we promise to make this so simple you'll lose all fear and remember it for life. So we think light is light, right? A wave. It spreads out. But let me ask you a fundamental question. Why does the color of light matter so much more than its brightness in certain experiments, like when light hits a metal?
That feels wrong. I mean, it's counterintuitive. I always thought brighter light means more power, more energy.
Yeah.
So you should do more work, shouldn't it?
Exactly. That's perfect classical thinking. But here is the surprising example that breaks everything. You can stand under an incredibly bright, hot red lamp for hours. I mean, massive intensity. And it won't cause a sunburn.
Okay.
But a very faint source of invisible ultraviolet light, which is just a higher frequency, can cause skin damage almost immediately. Why does the powerful red light fail while the faint UV light succeeds?
So the huge energy of the red light is useless, but the tiny bit of energy from the UV light works instantly.
Precisely. The answer to that puzzle is the key to understanding the photon. Okay, let's unpack this. The core idea is that light cannot be purely a wave or purely a particle. It's somehow both. This is the dual nature. And the old wave idea fails spectacularly for phenomena like this photoelectric effect.
But how can something be both? I mean, a wave spreads out, it's everywhere at once, a particle is localized, it's here. They seem like total opposites.
They do. And that's the quantum weirdness. Let's use an analogy to build a mental picture. The concert door analogy. Think of it like this. The metal surface is the door to a very exclusive concert. And the rule for entry is based on frequency. Think of frequency as a height requirement.
A height requirement, like at an amusement park ride.
Exactly like that. If you are too short, which is like low-frequency red light, you simply cannot enter. It doesn't matter how many short friends you bring with you, a huge crowd of short people still can't get in.
Ah, so the number of friends is the intensity, the brightness of the light.
You've got it. High intensity is just a lot of photons. But one sufficiently tall person, a single high-frequency violet or UV photon.
They get in instantly.
Instantly. This height requirement for the metal has a technical name. It's called the work function. We denote it by phi.
So that's the minimum energy needed to rip an electron out of the metal.
Yes. Our mental image has to be this. Photons are like discrete, high-energy arrows, not a continuous wave. They hit the metal surface and transfer all their energy in one single instantaneous transaction, a one-to-one hit.
So a dim light of the correct color is effective, but a super bright light of the wrong color is completely useless. The whole idea from waves, that energy just slowly builds up. That doesn't apply at all.
Absolutely correct. And that's what the experiments confirmed. The maximum kinetic energy of the ejected electron is completely independent of the light's intensity. That one fact killed the classical wave theory. It forced Einstein to propose this particle picture. Now, let us see how Ensert formally defines this, using the concepts of energy and momentum.
Okay, I have the textbook here.
Could you read out the definition for us? It's a bit dense, but very important.
Yes. It says, each photon has energy E equals h nu, and momentum P equals h nu by c, and speed c, the speed of light. All photons of light of a particular frequency nu, or wavelength lambda, have the same energy. D equals h nu equals hc by lambda, and momentum P equals h nu by c equals h by lambda, whatever the intensity of radiation may be.
Very good. See, that paragraph is packed with physics. Let's simplify it, step by step. Step 1. The energy of light isn't a continuous flow. It comes in discrete bundles, packets, or quanta. We call these quanta of light, photons. And the energy of each photon is given by that simple formula E equals h nu, where h is Planck's constant.
And that h is just a constant of proportionality.
It's much more than that. It's the fundamental constant of the quantum world. It's the bridge that connects the wave property, frequency nu, to the particle property, energy E. Now, step 2. When one photon hits one electron, it's an all-or-nothing deal. It transfers its entire energy, h nu. The electron uses some of that energy, the work function phi, just to escape the metal, and whatever is left over becomes its kinetic energy, the energy of its motion.
Okay, so the energy in h nu equals the energy to get out, phi plus the leftover kinetic energy.
Exactly.
Yeah.
And that gives us Einstein's photoelectric equation. Ke max equals h nu minus phi naught. This one beautiful equation explains everything. The frequency threshold, the instant emission, the intensity independence, everything.
So if I increase the intensity, I'm just increasing the number of photons, so more electrons come out. but the energy of each one stays the same because h nu hasn't changed.
Perfect. You've understood it completely. More photons means more electrons, which is a higher current, but the speed of each electron depends only on the photon's frequency. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Okay, now for step 3. This is the really mind-bending part. If a photon is a particle, it must have momentum.
Wait, but photons are massless.
Yeah,
They have zero Russ mass, and classical momentum is P equals mvc, so zero mass should mean zero momentum.
in the classical world, yes. But photons travel at the speed of light, c, so we have to use relativity. The relativistic formula is E equals pc. So the photon's momentum is simply its energy divided by the speed of light, P equals E by c.
That's really strange. How can something with no mass have a physical push? What is even carrying the momentum?
The energy itself. The energy of the electromagnetic field is carrying the momentum, and if you substitute E equals h nu and c equals nu lambda, the formula simplifies to something beautiful. P equals h over lambda. Momentum is linked to wavelength. And this isn't just theory. This momentum transfer causes a real measurable force called radiation pressure. Experiments like Compton scattering show photons colliding with electrons just like billiard balls. It's real. Let's do a quick calculation just to see the numbers. Suppose a laser pointer has a frequency of 6 times 10 to the 14 hertz. What's the energy of one single photon from it? We use E equals h e nu, so E equals 6.63 into 10 to the minus 34 times 6 into 10 to the 14. That gives us about 3.98 into 10 to the minus 19 joules. An incredibly tiny number.
So that's the punch, packed by one photon, so small.
It is, and that's why we don't notice these quantum effects in our big everyday world. And here's the final connection. Once we proved light, a wave can act like a particle. A physicist named Louis de Broglie thought, well, for symmetry, maybe particles like electrons can act like waves.
So matter can have a wavelength.
Yes. He proposed that the wavelength would be lambda equaled h over p, the exact same relation as for the photon. And that's the bridge to our next topic. Okay, now, let's tackle the silent killers, the common mistakes that cost marks in the exam. First one. Students visualize photons as miniature bullets, tiny little hard spheres.
Yeah, that's kind of how I was picturing them.
It's a tempting picture, but it's wrong. Photons are not classical bullets. They are quantum entities. They have no rest mass, they always travel at speed c, and they have both wave and particle properties. Don't get stuck on the bullet analogy.
So I should think of them as packets of energy, not tiny things.
Exactly, a discrete unit of interaction. That's a much safer way to think about it. Second killer, confusing intensity and frequency.
Right.
The wrong idea is thinking that if you make the light brighter, the electrons will fly out faster, with more kinetic energy.
But that's wrong. Kinetic energy depends only on frequency, the h nu part.
Correct. Intensity only controls the number of electrons, the photocurrent, not the speed of any single one.
Got it. Frequency is the gatekeeper for energy. Intensity is just the number of people at the gate.
Perfect analogy. Third killer. This one is a bit subtle. It's about momentum in the photoelectric effect versus the Compton effect. Students think since momentum is conserved in Compton scattering, it must be the main thing in the photoelectric effect too.
But it's not.
It's not the primary interaction.
Yeah.
In the photoelectric effect, the photon's energy is the main thing, used to overcome the work function. Momentum transfer is negligible. But in Compton scattering, the electron is free, and it's a true collision where both energy and momentum are conserved, like billiard balls. They are different processes. Okay, to lock all this in for the exam, let's use our memory anchors. For the two main formulas, the mnemonic is simple. Photon properties, E equals h nu, P equals h over lambda. Both use Planck's constant h, linking the particle side to the wave side. And a catchy phrase to remember the momentum part is, massless but mighty. Photons push with E over c.
Massless but mighty. Photons push with E over c. I like that.
And finally, a physical gesture for radiation pressure. Just push forward firmly with the palm of your hand. Imagine that slight constant push. That's the force from countless massless photons. That's what drives solar sails in space. So to summarize our deep dive into the photon, 3 key points. Firstly, light is not a pure wave. It consists of discrete energy packets called photons, and each one has an energy E equals h nu.
Depends only on frequency, not intensity.
Correct. Secondly, photons are real quantum particles that carry momentum, P equals h over lambda. This is proven by things like Compton scattering and radiation pressure. And thirdly, the photon proved that wave-particle duality is fundamental. The experiment you do decides which face of reality wave or particle you get to see. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam.com, right?
That is correct. Thank you for joining us for this in-depth concept explainer. All the very best for your studies.